Hey, welcome to Calculus. Today we're looking at 2.1 rates of change and limits. So the thing to remember about at least this first chapter is that there's a lot of abstract ideas going on here, but they're really building up to this one big idea called derivatives. So in calculus, the whole first semester, we're building this idea up of derivatives, and what that idea is we're trying to find, we're used to finding slopes between 2 points, right? So if we look at this graph here of f of t, we have 2 points on here. So on this function, we can find the average rate of change between these 2 points, right? We can find the slope between these 2 points pretty easily. This is kind of like an Algebra 1 type problem, maybe Algebra 2. But this idea that calculus is building into in the first semester is we're trying to find the slope at 1 point. And that would represent, rather than the average rate of change, right? If we're trying to find the change in speed between these 2 points, that's easy to find, right? We find the rise over the run, or the change in y over change in x, right? That's the idea of slope between 2 points. You guys have been working on it since Algebra 1. But what we're trying to do by finding the rate of change at a single point is it's going to give us the instantaneous rate of change. So if we're talking about driving a car, you can figure out how fast your car is going at any time, which is pretty cool, right? Rather than having to find the average of your average rate of change between 2 points. All right, so this would be the change in y, right? The vertical change, and this would represent the change in x. Right, which again we said is the same thing as slope. That's what you've been talking. That's the slope, quote unquote slope, that we've been talking about from Algebra 1 forward. Now, this form here, f of t plus delta t, which is the change in time, minus f of t over delta t, that's what we're going to kind of be looking at. So it's really complex, but it's just another form of this change in y over change in x, or the rise over the run. It's just in a different form. And the reason why we use the delta t is because we're trying to take that and make it equal to 0. But we'll talk about that further a little bit later. Okay, the big thing today we're looking at is average rate of average speed, or average rate of change. So for the first example, it says a rock falls off a cliff. What is the average speed for the first 2 seconds? So the interval we're looking at here is from 0 to 2 seconds. Right, so we can think about it as 16 times 2 squared minus 16 times 0 squared over 2 minus 0. So this is just the change in the y over the change in the x. Right, so we're looking at the end. Where is it at the end? Where is it at the start? And then how much time has passed? 2 minus 0, which is 2 seconds. Okay, so let's kind of simplify this up. So 2 squared is 4 times 16 is 64. Minus 0 over 2 minus 0 is 2. So then 64 divided by 2 is 32. Well, it doesn't say the unit, so let's say this is in, I think 16 is for feet, yeah. So feet per second. So on average, between 0 and 2, it was traveling at 32 feet per second. Now, that doesn't tell us exactly how fast it was going at any time, but over the course of those 2 seconds, its average speed was 32 feet per second. Okay, so now here's the cool part. Let's find the instantaneous speed. Instantaneous speed at t equals 2. So we're going to use that formula. We're going to use a little bit modified version. So let's say that what we're trying to do here is we're trying to find the limit as h approaches 0 of, f of x plus h minus f of x over h. All right, so this seems a little bit weird, right? Now, how is this related to our average rate of change, and why we're finding the limit as we approach 0? So let's say we have this parabola, right? And this represents our speed, right? So we know that it was, what was it, 16 t squared. This is our equation for our speed. So if we're looking at this parabola, if we're looking at this parabola at 2, let's say, right? Let's change colors here. Okay, so that's t equals 2. What we're doing is we're putting another point in here. We're not sure where the point is. We don't really care where the point is. But what we're trying to do is because we're doing the limit, right? We're trying to get this h ever and ever closer to the point, right? So that it gives us our exact problem. And let me kind of demonstrate to you what it looks like in Desmos. Okay, so let's say we have y equals 16. We don't have t, but we'll say x squared. Okay, so we have this parabola. We can zoom in. We can check it out, right? We can even find what happens when t equals 2. It's kind of a crappy graph to look at it, but let's change this a little bit just so that we can see it a little easier. Okay, so because we're looking at a parabola, it doesn't make too much of a difference, but we could find exactly where our point is at 2, right? All right, so what we're trying to do is let's find the slope. Let's find the average rate of change. So let's say we have, where's my equation? Okay, let's say we want to add a line there. So let's say that we have, let me figure this out in my head. So if we're looking at 2, then let's say we have 2, 4 is our point here. I don't know why our point's not sticking there, but yeah, 2, 4 would be our point on the parabola at 2. And then let's say our slope there is, well, let's not even find the slope. Let's find the average rate of change. So we're going to find the point between 0 and 2. So the slope from 0 and 2 would be 2. So let's say y equals 2x. Okay, so what we're looking at here is we're looking at the instantaneous, or the average rate of change between 0, the starting point, and 2, right? And that's represented by the purple line. So we can turn it off, we can turn it on. So that's representing the average rate of change. What we're trying to do here is we're trying to get it ever and ever closer. So let's say we had a different line here. I'm going to have to calculate it in my head, but it's going to be slope 3 and passing to -2. Okay, so let's do another one. Let's do y equals 3x minus 2. Okay, so notice that this one here is the average rate of change of the slope between the 0.11 and the 0.24. Right, so it's changing, and what we're doing is we're trying to move this ever and ever closer to 2 so that we can find the instantaneous rate of change there, if that makes sense. So each time we're getting closer and closer to 2, that's what the h represents. So that's why when we do our limit here, we're doing limit as h approaches 0. Right, so we're just kind of building this idea, and the sad part about this is the foundation for finding the instantaneous rate of change, but when you actually learn how to do it, it's really fast and easy. So yeah, this is just like the headache part of it, but it's very important for you guys to understand how they built this idea of a instantaneous rate of change. Okay, so we're gonna go put this together. So let's do different color here. We're gonna do f of x plus h, so we're gonna do 16 times 2 plus h, right? Because it's saying at t equals 2, so we're plugging in our 2 here and our 2 there. And then we're squaring it minus the f of 2, so 16 times 2 squared over h. Now, the thing to remember here is that anytime we're doing a limit, you're allowed to plug in the number if you can. However, if we're to plug in the 0 for h here, our denominator would be 0, and therefore we'd break our math. So we're not allowed to plug in h yet, but what we're trying to do here is we're trying to use some algebra, right? So we're going to do some algebra, we're going to try to simplify it out, and hopefully at some point we're going to be able to plug in that 0 for our h. We just can't do it yet because the h is in the denominator. All right, so let's go ahead and do this squared part here. Well, yeah, let's do the squared part. So we have limit as h approaches 0. We're going to square this thing. So 2 plus h squared. And I'm going to go through it really quickly because I'm going to assume that we know how to algebra, right? So we'd multiply 2 times h, so that 2 times 2 squared is 4. And then, or sorry, 2 times 2 is 4. 2 times h is 2. H times 2 is 2. So we have 4h, and then we have our h squared. Right, so that's the same thing as if we just did 2 plus h times 2 plus h and distributed, right? So we skip that step because we assume people can algebra. Okay? And then we have minus, well, let's do the math on this part. 2 squared is 4 times 16 is 64 over h. So check, we still can't plug in for h because h is still in the denominator. That sucks. But let's just continue algebraing or simplifying. Maybe let's change color again. Okay, so let's distribute this. So we have 16 times 4 is 64. 16 times 4h is 64h. And then 16 times h squared is 16h squared minus 64 over h. Okay, still can't plug in, but what we can do is 64 minus 64 is 0. So that's nice, right? And what we have going on, I might be running out of room, but let's try to fit it all in here to keep it neat. 64h plus 16h squared. 64h plus 16h squared is left over, divided by h. Now remember, anytime we have division with one thing on the bottom, we can separate this into two things, or we can just divide by h. So 64h divided by h is 64. And then 16h squared divided by h is going to be 16h. Now that we don't have our h in the denominator, right, because we canceled our h's out on the top and bottom, now we can plug in our 0. So this whole thing is going to be 64 plus 16 times 0, which is 64. Okay, so at that exact moment, at t equals 2, when the time is 2 seconds, it's going to be traveling 64 feet per second. So what calculus allows us to do is find instantaneous rates of speed. So that's like a huge, huge thing. We're no longer having to find the average rate. We don't need 2 times. We can find it exactly at any moment how fast something is traveling. And that's one of the huge ideas of calculus. All right, and again, this algebra stuff, a lot of people get hung up on algebra in calculus, which is sad, but it's necessary and it's good practice. So we're going to keep practicing it and get better at it. But yeah, eventually all this algebra is gonna, I'm not gonna say go away, but it's gonna be easier because we're not gonna have to apply the algebra. There's rules to find the derivative, the instantaneous rate of speed, or the tangent line. Okay, so some of the properties here, this is taken straight from your book, and all these 4 or 3 rules, I guess they're lumping in sum and difference. All these 3 rules is saying that if we are finding the limit of something, multiplication, subtraction, division, oh, here's the quotient rule. We can take that as 2 separate limits. So that's all it's saying. So if I'm taking the limit of, as x approaches something, 1, of 3x times 4x squared, for example, right? Then we can take the limit separately. We can do the limit of 3x as x approaches 1, and then we're going to multiply with that with the limit of 4x squared as x approaches 1, right? So we can take them separately. So sum, difference, product, quotient. You can find them as separate limits. And then the constant multiplication rule, number 4, that's just saying if we have a constant in there, we can take the constant out and find the limit of just the function. Okay, which is nice and handy. It's just something that you can do. Okay, so let's use that concept to find the limit as x approaches 0 of tangent x over x. Right, that looks complicated. Oh, there's some trig going on in there, and we can't plug in 0, right? Because if we plugged in 0, then we'd have an undefined function. So the first thing to remember is substitute the value for limit if possible. Right, that is going to save us our algebra if we can just plug in our number and then get an answer, because we're not going to have to do all the other stuff if we can just plug it in. So the reason why we're going to have to kind of manipulate this a little bit is because we need to be able to figure out what this value is. If we're not allowed to substitute 0 in for x just yet. Okay, so what we're going to do here is we're going to change our tangent. We know that tangent is the same thing as sine x over cosine x. Right, and then rather than say divided by x, well, we could just call that 1 over x. Right, so this is our tangent, and this is our divided by x. So this is the tangent, and this is divided by x. So we just changed it into a different form. Now, keep in mind, we're still not allowed to plug in a 0 there, right? If we plug in a 0, we don't get an answer. We have an undefined value there, and that's just not going to work out for us because that breaks math rules. Now, what we can do, though, is we can combine different things so that we do have an answer. So what we're going to do is we're going to combine sine x over x. Now, keep in mind, this is one of the things that you probably want to remember, that when we do the limit as x approaches 0 of sine x over x, we're going to get an actual answer. It's not going to be undefined. So that's going to help us. And then let's do limit as x approaches 0 of cosine over x. So we're just applying that the product property, and we're just separating this into 2, or we should say 1 over cosine of x. We're separating this into 2 different limits. All right, so let's talk about sine x over x. In fact, let's look at a graph of it. Let's go to Desmos. And we're going to prove this later on using squeeze theorem, but we're going to just kind of look at what sine x over x is. So let's go to trig, sine x oops, that's not divided by x. Okay, so that might not have an actual value there. In fact, if I plug in, if I touch there, oops, you can see at 0, our sign is undefined, sign x over x is undefined, right? Because we can't plug in a 0. But we can find the limit of that, and the limit of that would be 1, right? It's approaching 1 as we get closer and closer to 0. So the answer for this one, let's go back here. So this whole limit here, anytime we approach, as x approaches 0, sine x over x, that whole thing is going to be 1. Now, this one here, cosine at 0, is also 1. Right? So 1 over 1 is this whole limit. So 1 times 1 is going to be 1. So this whole thing, the limit as x approaches 0 of tangent x over x is going to be 1. Okay, next example, use a graph to explore whether the limit as x approaches 2 of x cubed minus 1 over x minus 2 exists. We can use a graphing calculator. You can use your graphing calculator to do this. I'm not sure if you guys all have one yet, but I have like a thing here that's supposed to be similar, because I can't show you what my calculator looks like from my iPad. But let's do this. What was it? Let's go back here. X cubed minus 1 over x minus 2. So what we're going to do in your graphing calculator, you're going to hit y equals, which is on the top left. It's going to get you to something that looks like this. So we're going to plug in our equations. X cubed. So we're going to do this button for x. And then you're going to hit caret cubed. You're going to shift over because we don't want to be in the exponent anymore. Minus 1. And then you're going to go into the second one. And then you're going to do x squared. Or sorry, no, we're not going to go into the next one. That's all divided by. It's because I'll put parentheses x cubed minus 1. That's your numerator. Divided by parentheses again. X minus 2. And then you're going to hit graph, which is all the way in the upper right. So we're going to hit graph. It's kind of hard to see, so we can zoom it in. Now keep in mind, if you guys like using Desmos, you're free to use Desmos. However, on your test, you're going to have to use your graphing calculator. So in class, if you have questions about it, we can practice it. But because we're limited in what we can do, what I can show you in our videos, we're going to have to try to use this this method. All right, so if we look at 2, is there a limit as x approaches 2? It's hard to see on this graph. There does appear to be a limit as x approaches 2. It looks like it's going to be 0. Okay, so let's go over here. The limit as x approaches 2 of x cubed minus 1, x minus 2 is 2. So you're just going to graph it. You're going to try to figure out where the graph is at 2, even though you can't click directly on it, and tell me what the value looks like it's approaching. Now, if we were to do that in Desmos, it's a lot nicer. But again, you're gonna have to use your calculator on your test. So we're gonna try to get comfortable with our calculator. But just to show us just to show what it looks like. Oops. X cubed minus 1 this one looks a little bit different. That looks like it's an asymptote too. Okay, so actually maybe the graphing calculator I'm using is terrible, but if you're using your TI-84 that we issued you, then you should be okay. This one actually is no, it doesn't exist. So maybe there's something wrong with my calculator, but your calculator should show the same thing and you'd answer the same thing as well. Okay. Next one. So now we're looking at limits overall. So the thing to remember here is that the limit exists if left and right agree. So we are going to find what this value is approaching from the left side, what's approaching from the right side, and we're going to say that if they're the same, then we have an overall limit. So we're just using this simple graph here. It's showing y equals f of x. So the first thing is at 0. So at 0, what's happening here? Well, we can't look at left and right because that's the end of the graph, right? So what it's telling us to do here is we're finding the limit as x approaches 0, and the plus means from the positive side. So it's meaning we're moving from the positive side towards this 0. So the value of our function here is going to be 1. The limit as x approaches 0 is 1. Okay, so the next point we're going to be looking at is at 1. So as the limit as x approaches 1 from the negative side. So from the negative side, let me erase this a little bit and change colors. Okay, so we're headed towards 1, but we're headed towards 1 from the negative side. Well, that's approaching 0, right? So the limit is 0. Now from the right-hand side, right, the positive side, as we go towards 1, well, that's the graph of the top one. So that's approaching 1. So the overall limit as x approaches 1 does not exist, right? Because one side we're approaching 0, the other side we're approaching 1. Therefore, overall, our limit does not exist. Okay, let's erase this up again. Okay, the next point of interest is at 2. So here's your 2. Now the limit as x approaches 2 from the negative side, all right, so coming from the negative side towards 2, well, that limit is going to be 1. This time we're doing as x approaches 2 from the positive side. That's also going to be 1. So the limit here is equal to 1 because they agree, right? This is 1, this is 1. Now keep in mind the actual value here of the function is going to be 2. But the limit we're talking about, because we're saying what are we approaching, what number are we approaching as we head towards 2 is actually 1. Okay, the next one, let's erase. Next point of interest is at 3. All right, so we're moving towards here from the negative side. That's going to be 2. If we're moving over here from the positive side towards 3, that's also 2. And then we know that the limit overall is 2 because the left and right side head towards the same point. Okay, and the last thing here is at 4. The last point of interest is at 4. we can't approach from both sides because the graph stops at 4, right? So we can approach from the negative side though. And as we approach from the negative side, then the limit is 1. Okay, so notice the only place where a limit does not exist is at 1. Right? Every other place we could find a limit. Now, the reason we're talking about limits and stuff like that is because we're going to talk about continuity soon, and continuity is a big caveat, I guess you might say, to a lot of the theorems in calculus, because it only works over continuous intervals. So yeah, the limits and stuff, you're going to use them to build the idea of derivatives, but we're also using them to talk about continuity. Okay, so here goes the squeeze theorem. So we're trying to find the limit as x approaches 0 of x squared times sine of 1 over x. Now, the squeeze theorem is a bit complex, but it's very elegant in its thinking. So notice we can't just plug in 0, right? We said that, all right, if we're allowed to do limit and we plug in the number and it comes out, we're good. But we're not allowed to plug in a 0 here because we have 1 over what would be 0 if we substituted it, and that would break our math again. Right, so we can't just plug it in here, but we can use the squeeze theorem, and we're focusing on first just this thing here. So the sign of any number, right? We don't even care about the 1 over x, but what we know about the sign of anything, right? We know the sign is a continuous function. It looks like that, right? So 1 over x, what we know that is that the values for any sign we can have, the greatest value would be 1, right? And the lowest value we could have is -1, right? That's just one of the properties of sine. So we know that our sine 1 over x, the maximum it could be is 1, and the minimum it could be would be -1. So that's just a fact. That's a property of the sine function. Okay, so what we're going to do is we're going to modify this a little bit. So let's do a different color here. So what we're saying is that, all right, I need this to look exactly like that top so we can find the limit. So let's do, let's multiply x squared in here. But if we're going to do that, right, we have to multiply on the outsides too. That's just algebra. What we do on one side, we do on all sides. So we're going to do -1 times x squared, and we're going to do positive 1 times x squared. All right, so all we did here was multiply by x squared to each part of our inequality, right? The outside, the right side, the middle. Okay, so here's the cool thing here. Right, we're not going to change the inside here, but what we're going to do is we're going to substitute. So we're trying to find the limit as x goes to 0 of this whole thing. We're going to substitute in here. So -1 times 0 squared. And then we're going to substitute 0 here. So notice that this is 0. Right? -1 times 0 is 0. And then it's 0 here, because 0 squared is 0. So now that we know that this whole thing is between 0 and 0, therefore 3 dots, ergo x squared sine 1 over x, well, we should say limit as x goes to 0 of that whole thing has got to be equal to 0. If it's between 0 and 0, then it's equal to 0. So very elegant. It's kind of one of those things that it's higher levels of thinking and of calculus, but they do sometimes ask it on the test. In fact, you should expect some squeeze theorem on the test. So yeah, it's good that we cover it now. It's going to pop up here and there throughout calculus, but it's something that you guys need to know, because otherwise there's no other way to find the um, the limit here. Okay. All right, that's it for today. Awesome. So again, just a quick review of things that we covered, because it was a lot. And I apologize, but we've got to keep pace here, especially this year, because the end of course exam for calculus is May 4th, and we have some wiggle room here, but not much. So I'm going to try to go as fast as we can, and hopefully you having the videos in front of you is going to help you to do your to understand the concepts and to do your work a little bit easier. But yeah, we got a lot of stuff to cover in a little amount of time, so we're just going to try to go quickly. We do have some leeway, so we can stop and cover some ideas if you need to over again. But we don't have that many days to slow down, so we're going to try to go as fast as possible, and so that we have some time at the end maybe to do our review for your calc exam. Okay, so yeah, again, just a review. So we started off with this idea of average rate of change. It's the same thing as slope. It's the change in y over change in x. We're finding the slope between 2 points. That's the big idea. That's from Algebra 1, right? So we did some of that. Then we talked about, all right, what if we wanted to find the speed at a single point? And then we use this thing here, this monstrosity, right, with the limit. So we said the limit as h approaches 0 of f of x plus h minus f of x divided by h. And the whole thing here was that we need to do a lot of algebra, right? All this algebra here until the point where we could plug in our 0 from h, meaning that there'd be no distance between the 2 points. The points would be overlapping, and then we just have t equals 2 and the slope at that point. Okay, so that's the beginning of our derivative idea. And we said that, yeah, the algebra sucks on it, but we're going to get good at it because you're going to have to do it. And eventually, though, it's going to be a lot easier. Okay, then we talked about the properties of limits and how we could use them to find limits, right? So the tangent x over x, we couldn't just plug in our 0, so we need to find a different way. So we applied the math on it. We said sine x over x times the limit of 1 over cosine x, right? And then we found those two limits individually, and then we found that the overall limit for the tangent x over x is 1. So another way to find the limit by using some of the properties. We used the graphing calculator. We just kind of like basically looked at it, found the graph, and decided that it did not exist, right? Because there wasn't a number there. Okay, and then we talked about finding limits from the left side and right side, and we also said that the limit only exists overall if the left and right side have the same number, if they agree. Okay, and the last one, we just kind of went over the squeeze theorem. We got our introduction to squeeze theorem. It's a monster, but it's very elegant. It's awesome when we know how to apply it in the few cases that we can apply it to. All right, so if you have any questions, please bring them to class for next time. We can go over them. Hopefully we can clear up any questions you have then. All right, good job.